Hi everyone, in this video we are talking about section 3.4 from your textbook, and it's a little bit all over the place. So in section 3.4 we have a discussion about quartiles and percentiles, something called the z-score, and then lastly rules of thumb to know and memorize called the empirical rule. So for quartiles, we can represent the first and third quartiles of a given data set by using capital Q with subscript 1 for the first quartile, and then Q subscript 3 then for the third quartile. And what I want to point out here is this capital Q subscript 2, we don't actually use that symbol very much to mean the second quartile, because the second quartile would just be the median. So remember, x tilde is the symbol we use for the median. So let's talk about percentiles. I have an example for you. Suppose 3 million high school students took the PSAT college entrance exam this year in the United States. I want you to sort those PSAT scores from highest to lowest, and then recognize that if I have 3 million students, then 10% of 3 million is 300,000 students. And now consider the score of the student whose rank is number 300,000. So the student who didn't perform the best and didn't perform the second best, but performed the 300,000th best out of 3 million. It's pretty good, considering the sample size is 3 million. This score, whatever his test score was, his or her test score, this is what we call the 90th percentile. And so this is the notation we use for the 90th percentile, capital P subscript 90. And so like the 51st percentile would be capital P with subscript 51, for example. But anyways, this is the way that percentiles work. And so if you have like the 99th percentile, that's like a really, really good test score. That means you're better than 99% of the population, and you're only worse than 1% of the population. If you have a test score that's in the 40th percentile, that's doing okay. That means you're worse than 60% of the population, but you are better at that test than 40% of the population, right? So percentiles sort of tell you where you are relative towards the others. And just to keep things clear, I like to make it so that an increasing percentile means an increasing score or an increasing measurement, right? And so whenever you, let's say you're weighing babies, I think that's an example that's coming up here, the heavier the baby, then also the larger the percentile. So if a newborn was 12 pounds, you might say that's in the 98th percentile or something like this. If a newborn was like 4 pounds, you might say that's in the 5th percentile, right? So increasing measurement, increasing percentile. Here we have a little graphic that I want to explain so that I can use it as an example here in a moment. It's a distribution of family wealth that I got off of some website a while back. Here's the link if you want to see my source cited. But this is the distribution of family wealth in the United States as of 2016, it looks like. And so the way you would read this, and notice the x-axis, probably the reason I included this is because the x-axis is in percentile. The median would be the 50th percentile. So the median household wealth in the United States, we'll use x tilde to mean the median, is $97,000. And so I think what they mean by wealth is like, for a particular family household, add up the value of all of their assets. So their car, their house, their savings account, their retirement investing accounts. Subtract any debt that they have, so subtract student loan debt, subtract their car note if it's not paid, subtract their mortgage, how much they still owe on their house, subtract all their debts, And then what would you have for wealth, right? What would you have as somebody's net worth, or a whole family household's net worth in this case? So the median is 97,000. The 80th percentile would be about 500,000. And so if you're wondering, as far as family wealth goes, how many households in the United States have a net worth of more than 500,000? Well, it would be 20%, because everywhere between 80 and 100%, that represents about 20% of the population. So 20% of the households in the United States have more than $500,000 in wealth. Then you might wonder how many households in the United States have negative money, right? How many households' wealth is actually negative because their debts outweigh their assets. And so it's difficult to tell where 0 is, but it's probably somewhere around here for the 15th percentile. So that means about 15% of the population don't have any wealth at all. And it grows very, 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 very slowly, of course, until you reach really the top percentiles. And this is what a lot of people complain about, or they used to complain about this very frequently. What people complain about is that if you were to just look at the 99th percentile, and actually I guess the way that this graph is made, it doesn't really show you the width of the slice for the 99th percentile. I guess what I just showed you is the 98th percentile. But if you look at the 99th percentile, the top 1%, and another way to say the top 1% is to say the 99th percentile, they own 38.5% of the wealth in the United States. So anyways, this is a neat graph, I think, because it shows you an application of percentiles, and you can see where you land. If you personally know that your amount of wealth was somewhat, maybe just a little bit larger than 10,000, then looking at this graph, you could say, well, I'm somewhere between the 25th and 30th percentile. So you have more wealth than 25 to 30% of the United States, but also less wealth than about 70% of the United States. It's a way to compare one measurement in your data to the rest of the data. Yeah, so again, this slide is just kind of restating what I've already stated, that there's a lot of people in the United States. In the United States, there's 328 million total residents. And so 1% of that 328 million would be about 3.28 million. And if you were to ask, ranking the people from wealthiest to poorest, right? So I can have my words flip-flop here. But if you're going to rank people from wealthiest to poorest, the person with rank number 3,280,000, that amount of wealth, that would be what we consider the 99th percentile. So, and this graph doesn't perfectly correspond because this is talking about family wealth, not individual wealth, but you get the idea. So, percentiles. The first quartile, remember Q1 is the first quartile. The first quartile is the 25th percentile. 25th. Man, my pen is a little bit difficult to draw with today. The 25th percentile and the percentile. Man, the 25th percentile and the first quartile are the same thing. And my handwriting is terrible. Percentile. Okay. The second quartile is the same thing as the 50th percentile, which is the same thing as the median. Remember, x tilde is the median. And then the third quartile and the 75th percentile are the same thing. Okay, so if you give birth, and then the doctor tells you your baby's weight is the 21st percentile, the question is your baby heavier than the median or lighter than the median? So remember, the median is the same thing as the 50th percentile. So this would mean your baby is lighter than the median. Okay, let's talk about z-score. So z-score is a test statistic. Each measurement in your data set has a z-score. So if you've taken 50 measurements, then each measurement having a z-score, that means you can calculate 50 different z-scores. Now, an actual z-score would involve the population mean, which we use the Greek letter mu to mean the population mean. Man, I'm really practicing my handwriting today. Population mean. Maybe if I make this pen not quite as thick. And it also uses the population standard deviation. And this is what we'd call an actual z-score. However, you may recall that in most situations we can never know parameters. So when we talk about population mean and population standard deviation, those are parameters that we probably don't know. And most likely you'll be using an estimated z-score, where you can just swap in the sample mean instead of the population mean, because after we collect our measurements, we can always calculate a sample mean, and we can always calculate a sample standard deviation for our data set. So it's much more likely that you're going to be using an estimated z-score in a lot of situations. But as long as we're talking theory, each measurement does have an actual z-score. It would just be impossible to calculate in most situations. Now the z-score is the number of standard deviations away from the mean. So notice up top, you're looking at the difference between the measurement and the mean. So measurement minus mean. It's also what we call a deviation. And then in the denominator, we have one standard deviation. So you're counting how many standard deviations am I away from the mean. You could think of this as a deviation divided by the standard deviation. So the larger the z-score, that means your measurement is farther from the mean if it has a large z-score. Or if it has a really large negative z-score, that would mean your measurement is far from the mean in the negative direction. So if you want to convert between z-score and percentile, and most of the time we can calculate our z-score, and then we want to convert our z-score into a percentile, there's a way to do this that you can use in both Excel and in your TI-84 calculator. I'll just briefly demonstrate both of those to you. Starting with Excel, if I can get Excel to load. Almost there. So Excel, there's a formula. It's norm.dist. And so if I calculate maybe some z-score, and to calculate a z-score, what do we need? We need like a mean. It could be a sample mean or a population mean, depending on the situation. We need some kind of mean. We need some kind of standard deviation. And then we need a measurement value. So let's say our mean is 12.2, our standard deviation is 3.1, and our measurement value is going to be 17.5. Then our z-score is going to be, in the numerator, the difference between the measurement and the mean divided by the sample standard deviation. So the deviation, you could talk about the measurement, deviation as being just the difference between the measurement and the mean, how much the measurement deviated from the sample mean. And then our z-score is just the ratio of that deviation to the standard deviation. So deviation divided by standard deviation. That'd be our estimated z-score. And if I want to convert this to a percentile, so if I want to take the percentile of that particular measurement, then what I would do is I'm going to type in equals norm.dist, open parentheses, put in your z-score there, comma 0, comma 1, comma true, and then multiply times 100. So my measurement percentile, it looks like we're in the 95.6 percentile. You could round up and say it's the 96th percentile. And if you don't want to multiply by 100 at the end of your formula, here's another thing you can do in Excel. Get rid of that 100, so it says 0.95 as a decimal, and then go up here on the ribbon to this percent button, and you can just click that. And it looks like our percentile is the 96th percentile for this particular measurement, because it's so far away from the mean. Okay. So this is converting from z-score to percentile, and this whole process sort of assumes a normal distribution of your data. And we haven't discussed yet in class what a normal distribution is, but we will actually later this video. We will here in a moment. Now let's do this on a TI-84 calculator. So here's my TI-84. Let me exit out of all this. And let me clear the memory by doing second plus 712. Okay. So blank slate calculator. If I want to calculate a percentile after I have already found my z-score, what I will do is go to second, and then the button that says VARS. So actually what we're selecting here is the DISTR, which stands for distribution. But to get to the distribution, since it's in blue font on this calculator, we have to press the second button first. And then second VARS will get us to the distributions. That didn't do what I wanted to do. I think it went to the VARS actually, so quit. And second VARS again. Now we're in the distributions. So let me go to number 2, which says normal CDF. CDF here stands for cumulative distribution function. That's not important for you to know yet, but might as well explain what the little letters are. So we're going to number 2. We click enter. It pops this screen up, and on your calculator, I want you to never, ever, ever use the lower thing, right? So don't mess with that. We always want to leave lower as being -1 E99. Where it says upper, this is where we're going to put in our z-score. And our z-score on my example, let's see what we put, was 1.7. Let's do a z-score of 1.7 again. We leave the 0 and the 1 alone for calculating z-score. We scroll down to paste and we do enter and then enter again. And this tells me 0.955. And if I multiply that number by 100, I can get my percentile. So it looks like the percentile is again the 96th percentile. So that's how you do it on your TI-84 calculator. I'll mark up this slide so you don't forget where to put the z-score. It's going to go right here. It needs to look more like an O, a little bit less like a sigma. Okay. Now, here's an example. Suppose you have a 3-month-old female baby. She weighs 15 pounds. Suppose the average 3-month-old female baby is this, and notice this is a sample mean because I'm talking about the average. It's 12.9 pounds. Let's suppose the weight of female 3-month-old babies is normally distributed with a standard deviation of 2.2. So standard deviation has the same units of measure as the measurement, so that's 2.2 pounds. What is your baby's percentile if your baby is 15 pounds? Well, we first calculate the z-score, which is going to be the deviation, the difference between your measurement and the mean, 15 minus 12.9 in this case, divided by the standard deviation, so divided by 2.2. So 15 minus 12.9 divided by, oops. In order to do this right, I can't just put divided by 2.2. It'll only divide the 12.9 by 2.2, so that won't be good. But I can click enter and then divide by 2.2 and get a z-score of 0.9545. And then, after I have the z-score, we know how to get our percentile. We go to second VARS, normal CDF, we leave lower alone. Upper is where our z-score goes, so 0.9545. We leave mu and sigma alone. We do paste, enter, and we get a percentile of the 83rd percentile. So the baby's percentile is the 83rd percentile. Okay. Now, for normally distributed data, the probability density function, which we abbreviate with PDF to mean probability density function, it's this. And I want to emphasize something here that you do not need to memorize. You don't need to memorize this, but I do want you to know that the shape of the normal distribution is given by a mathematical function. So it's not just something that you draw that looks approximately like a bell, but the bell shape actually comes about because there is a real mathematical function here, right? And so there's some characters here that you probably recognize. We have 1 divided by sigma. What is that sigma? That's the population standard deviation. So he's familiar to us. This is that number pi that you ran across in geometry relating to circles. This E is what we call Euler's number, so that's actually just a value. That's not a variable, but Euler's number, E, is something like 2.71828, and it has a decimal expansion that goes on forever, just like pi's. And then this is actually an exponent here. It's not super obvious because there's so much going on in the exponent. But this is actually e raised to the power -½ times x minus mu over sigma, all of that squared. So this is an exponent going on. It's just that there's so much going on in the exponent that it almost doesn't look like it's an exponent. But notice that it's a little bit raised up off of where the E starts. Okay. But of course mu, that's just the population mean. And then again we have that sigma appearing again. And so this is not impossible to understand if you really spend the time to appreciate it. And then I want you to notice here, in statistics, whenever you see hats on stuff, it means we're making a prediction or making an estimate. So hats on stuff means estimate. If I was going to estimate the PDF, estimate the probability density function, then whenever I write PDF, I'm going to write a little hat above it. So this is an estimation of the probability density function. And it's an estimation because instead of the population standard deviation, I'm going to put in what I can calculate, which is the sample standard deviation. And then instead of the population mean, instead I'll put in what I can calculate, which is the sample mean. So remember those sample mean and sample standard deviation, those are just statistics. And statistics are just estimations of their corresponding parameters. So that's what makes this an estimate of the true PDF, and that's why I put a little hat above it. Again, back to this page, don't bother memorizing these. Please don't. Okay. So, for normally distributed data, this is the PDF, which we talked about. And this is what it looks like. If you actually graph this on a little plane, where my vertical axis is values of the probability density, and my horizontal axis are values of x. This is what that graph looks like. And specifically, this is a graph for when the mean is 0 and the standard deviation is 1. But anyways, this curve in red is actually what it looks like if you get into Desmos.com and you plot this just as you see it. Now here's an example. Intelligence quotient, or IQ, was a scale developed specifically so that they would have a mean of 100 and a sample standard deviation, or a standard deviation of 15. So the way they create and score IQ tests is to actually hit these two parameters. And so we can use that as an assumption here. And we'll suppose that maybe you take an IQ test and you find out that your IQ is 130. We'll ask, what is your percentile? Remember, to find percentile, we first need the z-score. And so for you, your measurement of IQ is 130. We'll subtract from that the mean, which is 100, and then divide by the standard deviation, which is 15. So that's 30 over 15, which is just 2. If I want to get percentile from my z-score, then again, I'm going to go to second VARS, normal CDF, where it says upper, I'm going to put 2, because that's my z-score, paste, enter, and then it looks like I'm looking at the 97.7, or you could round up and say you're the 98th percentile for intelligence, which means you're smarter than 98% of the population and also not as smart as 2% of the population. And now we ask, how many people alive today would have an IQ that's greater than 175? And so let's kind of run through the same procedure here. The z-score for this particular measurement, for an IQ of 175, be 175 minus the mean, divided by the standard deviation, which is 5. Let's find the percentile. So second VARS, go down to normal CDF. The upper is going to be 5 this time, because that's my z-score I'm concerned with. So click paste, enter. And this is the percentile. It would be the 99.9999997 percentile. So basically an IQ of 175 is just extraordinary. But there are actually 8 billion people alive today. And so if you were going to find out how many people alive today have an IQ better than 175, well, first, I'm going to do 1 minus that number. So that means, if this is the 99.99997 percentile, that means that this number, which is 0.000000287, that's the decimal of the number of people who are more intelligent than an IQ of 175. And then let's multiply by 8 billion, which is just an approximation. It's just a guess of how many people are probably in the world today. And it turns out, if I round up to 2297, that means there's about 2,297 people alive in the entire world today that have that high of an IQ. And if you consider how large the world is, with 8 billion people, this is a very, very tiny number. It's a very tiny portion of the population that has an IQ that high. So it's very extraordinary. Okay. This is what a standard normal distribution looks like. This is the PDF function, or the probability distribution function. I want to point out that my X scale is going to be in terms of standard deviations. So sigma means standard deviation. And if we go 1 standard deviation to the right and 1 standard deviation to the left, basically we start at our mean and we either take 1 standard deviation to the left or 1 standard deviation to the right. The area underneath this red curve for this bounded region is 68% of the area of the whole curve. Let me write that out. The area in blue here is 68% of the total area under the curve. And I want to point out that the total area under curve, that represents something. The total area under the curve represents the whole population. So if I only consider the individuals in the population that have some measurement that's inside of this interval, from the mean minus 1 standard deviation up to the mean plus 1 standard deviation, that's still 68% of the whole population. If I extend this a little bit and I go up to this point, which is the mean plus 2 standard deviations, and I extend it down in this direction, so I get the mean minus 2 standard deviations, and I consider all of the area inside this bounded region, this is the area inside the bounded region divided by the total area under the curve. I guess I'll write area under curve like this. And basically what this is saying is the area in green here represents 95.4% of all the area under that curve. And so again, if this is some kind of measurement, and you take somebody's measurement and they have a measurement somewhere between the mean minus 2 standard deviations and the mean plus 2 standard deviations, that means they belong to this group. They're somewhat ordinary because 95.4% of the population is going to have a measurement in this area. If I extend it out to further, so the mean minus 3 and the mean plus 3 standard deviations, of course, we're shading in an area that's more and more of the total area under the curve. So in yellow here, we see 99.73%. It's almost all of the area under the curve, falls within 3 standard deviations of the mean. So that means it's really uncommon if you have a measurement that has a z-score that's either greater than 3 or less than -3. That would be actually kind of shocking to find one of those, right? If we extend it to 4 standard deviations in either direction from the mean, you can see we're getting closer and closer to 100%. And if I extend it to 5 in either direction, of course, that's practically 100% for almost any purpose. Of course, if you just draw a vertical line down the middle at the location of the mean of a normal distribution, half of the distribution will lie to the left, so the area under the curve to the left is 50%. And knowing that, taking the difference, or the distance, I guess the interval between the mean and the mean plus 1 standard deviation, all of the measurements that might fall in this region represent 34% of the population. And so if you add 50 plus 34, then you would find that 84% of the measurements are in this region, which is less than the mean plus 1 standard deviation. So you can sort of add and subtract these areas, right? 50% plus 34% is 84% when you combine the two. This would represent 47.7% from the mean to the mean plus 2 standard deviations. So if you add the other 50% of the curve to it, that's 97.7. 47.7 plus 50 is 97.7. And then extending it 3 standard deviations and then adding half, and I'm just showing you to be very, very clear about this. So a little summary here. Plus or minus 1 standard deviation gives you 68%, plus or minus 2 standard deviations, and then plus or minus 3 standard deviations. These are the most important values to know. And if you just want the one-sided little bits that fall in between these vertical black lines, of course it's 34%, 14%, 2.1%, and so on. So these slices are getting very small, and hopefully that's obvious from the numbers and from the graphic here. So this is what your textbook recommends that you memorize. So the interval that goes from the mean minus 1 standard deviation up to the mean plus 1 standard deviation, this interval represents 68% of the population. The interval that goes from the mean minus 2 standard deviations up to the mean plus 2 standard deviations represents 95.4%, and then the interval that goes from the mean minus 3 standard deviations up to the mean plus 3 standard deviations, that represents 99.73% of the population. And this is the end of the lesson, but I think that I've been using a mixture of parameters and statistics in my notation, and so I'm just going to go back here and correct this. So let's see, that should be a mu for population mean if I'm being picky, and I'll go ahead and finish this and upload these notes for you guys to see. Y'all have a good one. I'll see you in the next video.